Hi guys, this video covers the concept of a balanced binary search tree. So remember that earlier we analyzed the minimum and maximum height that's possible in a binary search tree, and we saw that the maximum height achievable is n minus 1, which is big O of n. You get that when you have a very unbalanced tree where every parent node only has one child, like on the right here. And then the minimum possible height that's achievable is this base 2 logarithm of n plus 1 minus 1 expression, which is big O of log n. It grows logarithmically. And you get that when every parent has exactly 2 children. So the height of a binary search tree is critically important for the efficiency of pretty much all the tree operations. Searching for a key takes time big O of h proportional to the height because that operation starts at the top and works its way down to a leaf in the worst case. Inserting a node also starts at the top and works its way down to a leaf always, so that's big O of h. And erase is the same thing. Searching for the node to erase takes big O of h time in the worst case. So if the height is linear in the worst case, then all of these runtimes become big O of n. And that's not a very impressive result because we saw at the beginning of our coverage of the map abstract data type that there's a very simple data structure called an association list that's just a vector of pairs that achieves linear time for all of these operations. So far, binary search tree doesn't look very good. However, if we can make sure that our binary search trees always have logarithmic height, which is the minimum achievable, then all of those operations become logarithmic. Searching, inserting, and erasing take big O of log n time, and that is much faster than linear time. So that's kind of the goal of self-balancing binary search trees. What does balance kind of mean? Well, intuitively, balance means that there's an equal number or approximately equal number of nodes on either side of any parent. So in the best possible case scenario, that's true everywhere. Every single node here has exactly 2 children on the 2 sides, except for the leaves at the bottom that have 0 children. We get imbalanced trees when there are an imbalance there, where a parent has a lot more nodes on one side than the other. For example, this is the worst case tree here. If we look at the balance situation at the root, there are 0 nodes on the left and all of the other nodes are on the right. And so that's a very imbalanced situation. It would be more balanced if it was more even, like about equal numbers on either side. We would call that right heavy. There's too many nodes on the right. Here's a more realistic example. It's still imbalanced. Here the root has 4 nodes on the left and 2 nodes on the right. So there's twice as many nodes on the left side than the right side. It's better than the worst case, but it's still not great, and we would call that imbalanced as well. That's left heavy because there's too many nodes on the left side relative to the right. So how can we do this, maintain balance? The term for a kind of binary search tree that achieves this is called a self-balancing binary search tree, self-balancing BST. The goal of a self-balancing BST is to maintain logarithmic height at all times. The way pretty much all of these work is that we start with a plain binary search tree that works the way we've talked about. And the operations that do not change the shape of the tree still work the same way. So searching works exactly the same way in a balanced tree. Creating an empty tree works pretty much the same way. You just create an empty tree with no nodes. And the size operation just returns the size of the tree, so on. The ones that don't have to deal with changing the shape of the nodes where they're located are exactly the same as plain binary search trees. The ones that are different are the operations that add or remove nodes. Those need to somehow maintain balance. So that would be the insert operation and the erase operation. We need to redesign those a little bit so that they do not create these very imbalanced trees. One widespread approach for achieving this is the balance invariant approach. It's not the only way. There's some other self-balanced binary search trees that achieve balance in a different way. For example, B trees and splay trees, they use different principles. But the approach that we're going to look at in our videos here is the most widespread approach, which is to introduce a balance invariant. A balance invariant is a rule for maintaining balance in the tree. This goes alongside the binary search tree order invariant that we've been working with for a while that says that all of the keys have to be in order, left to right. So what we do when we design a self-balancing binary search tree that uses this invariant approach is that we define for ourselves some rule for how the tree has to be shaped, and then we prove that any binary search tree that obeys that rule has logarithmic height. Then the insert and erase operations need to be amended to maintain balance. So they need to actually make sure that they obey this invariant at all times. Here's what the pseudocode for those might look like. So to insert a pair in a self-balancing tree with an invariant, we know at the beginning that we've got a tree that's obeying the invariant to begin with, because the rule is every operation has to keep the tree obeying the balance invariant. So to begin with, we've got a valid tree that's balanced. Then we do the plain binary search tree insert algorithm that we covered in previous videos. Remember, that returns true or false to tell us whether something changed. So if we did make a change and the invariant was just violated, then we do a restructuring to restore the invariant. So sometimes when we insert a new node, the tree is still balanced kind of miraculously, so we don't have to do anything, we're good. But other times, inserting that new node imbalances the tree, and then we have to go in and fix whatever rule we just broke that made the tree imbalanced. And erase is the same idea. To begin with, the invariant is obeyed. Then we do the plain binary search tree erase operation that we've covered previously. If that did make a change and we just imbalance the tree by removing a node, then we have to do this restructure operation to restore the invariant. And at the end of this, the invariant is definitely obeyed. If the plain erase or insert operation did not violate the invariant, then it's still true. If those operations did violate the invariant, then we fix it. So there are a whole lot of different approaches that use this general approach of defining an invariant and then maintaining it. Here is a list of some that are worth knowing about. One is the AVL tree, and the invariant on an AVL tree is that the height of two sibling nodes has to differ by less than or equal to 1. So two siblings can have the same height, or their heights can be off by 1, but they can't be different by more than 1. A weak AVL tree is a newer rendition of the AVL tree. It has a slightly looser invariant. It's a little bit more flexible, and it ends up being simpler for that. The red-black tree is a self-balancing tree that has an invariant defined in terms of node colors. Every color is called red or black, and basically the red ones don't count for balance purposes, and only less than half of the nodes are red, and the black nodes are perfectly balanced. So basically, if you ignore half of the nodes, it's a perfectly balanced tree. An AA tree is another one of these. It has nodes on levels, kind of like depth levels or height levels, and a right edge can be horizontal, but you can't have two horizontals in a row. And a crumple tree is one that myself and a co-author defined recently, and this is another one of these that puts nodes on levels, and the rule is that an edge between two nodes can only span 1 or 2 levels. It can't span 0 levels or 3 levels. So anyway, all of these invariants work. They all follow this pattern where every time we insert or remove a node, we check, did we just break the rule, whichever rule we're using? And if we broke the rule, we have to rearrange the nodes so that the rule is being followed again. And all of them guarantee logarithmic height, so they're efficient.